In this video, we will be discussing network and cloud technology. However, saying network technology might be a bit misleading, as a big part of what we're going to be talking about is the human element. As we've discussed in previous chapters, what makes networks valuable is not necessarily the technology behind them, but the number of people or participants that are part of the network. We call this the network effect, and that's whereby increasing the number of people in a network improves the value of that network. Consider, for example, YouTube, a popular video hosting website. The first person who signed up for a YouTube account likely didn't get much value from it. Sure, they could upload videos, but there is no one to share them with, and there's no other videos to watch. As more people started signing up for YouTube accounts, and sharing and watching videos, that network gained value, not only to the company that owned YouTube, but to the members of that network, as they now had others to share with and interact with. Before watching this video, I highly recommend reading Chapter 6, The Cloud, and trying some of the related MyLab MIS homework. Also, if you're really interested in a deeper exploration of the technologies used in networks in the cloud, I'd recommend reading Knowledge Extension 9 after watching this video. Today we're going to be concentrating on exploring these concepts at a high level. Knowledge Extension 9 will fill in more of the low-level details if you're interested. So let's get into it. We will begin our journey today by first discussing networks in general, and then moving on to cloud computing and its applications. But first, why are networks important, and why should you care about them? Well, networks are important because they enable collaboration. Collaboration, as I'm sure you're aware, is when two or more people work together to achieve a common goal, result, or product. When collaboration is done correctly, it produces results greater than what could be achieved by any individual working alone. And a big part of doing collaboration correctly is communicating effectively. Computer networks enable this communication and allow it to happen remotely over large distances. The effectiveness of this collaboration is driven by four critical factors. We've already mentioned communication, but it is more than just the method by which you communicate. It's having the required skills to communicate effectively. One of the most important skills businesses are looking for today in new hires is the ability to communicate and express your ideas competently. This is also largely cultural. Is your business fostering an environment where employees can freely give and receive critical feedback? Can they openly share and contribute new ideas? Do they have the tools they need to do this properly? All of this falls into communication side of collaboration. And this brings us to communication systems. Communication systems provide the technological tools to enable communication across an organization. These are the services and software such as phones, email, instant messaging, and video conferencing. These communication technologies have become especially important during the COVID-19 pandemic by enabling work from home through video conferencing applications such as Zoom and virtual private networks. We'll be getting a lot more into virtual private networks later in this video. This move to working from home is something that will not likely disappear anytime soon, and these communication systems will play an even greater role in the future. Employees are starting to demand the option of remote work, and businesses that don't properly invest in these tools and policies to enable this could be left behind or start facing significant labor shortages as employees move on to employers who do allow remote work. Next is content management. We covered content management systems, abbreviated as CMS, in Chapter 5. While they're a great tool to provide information to your potential customers, for your business website for example, they also play an important role internally. While communication systems handle the live or near-live communication in business, content management systems enable collaboration by providing a repository of documents, schedules, and information that can be easily shared or edited collaboratively within a business. This is far more than just a shared drive that employees dump in files into. A CMS has to handle multiple employees working on the same documents simultaneously, and prevent any conflicts that might arise from this editing. A good CMS also tracks changes, provides tools for finding relevant information, integrates with businesses' other information systems, and manages users' privileges and permissions. By privileges and permissions, I mean ensuring that employees can only read and write to documents they're authorized to. You wouldn't want anyone writing salary information, for example. The last major collaboration factor is workflow control. Workflow are the processes and procedures that are followed by employees to create, edit, use, or discard content in your CMS. These could be documents, or things like purchase orders, requests for quotations, or other business documents and forms. Workflow can also describe the flow of goods and services between employees to accomplish some goal or end product. This is distinct from the idea of business process, which we discussed in Chapter 2, as workflow is focused on the internal delivery of goods and services to employees, whereas business processes focus on delivering them externally to customers. The idea here is that we want to have a clear process or procedure for how a task leads into another. We need to know what task needs to be completed before we can do the next one, who is responsible for that task, and have a clear idea of what the steps are for completing the task. We'll talk more about information systems to support this when we get to Chapter 7, and discuss things like ERP, that's Enterprise Resource Planning, systems that enable cross-communication of these sort of processes and procedures across the whole organization. Moving on now to network externality. According to traditional economic theory, as the supply of a product increases, the price or value of that product falls. For example, at the start of the pandemic, the cost of things like personal protective equipment, hand sanitizer, and even things like toilet paper skyrocketed as it was in short supply and had a sudden demand. Now, as everyone has a small stockpile of masks, and mask mandates have been dropped, the price of masks have plummeted from the peak of the pandemic, as everyone has them, and there's no longer a large demand, but there is a large supply. However, this theory does not always hold. In certain cases, especially with service-based products, the value of a product can grow with the supply, or with the number of people that use that product. For example, let's say you're going out for dinner, but not yet sure what restaurant you're going to eat at. You drive by a row of restaurants on the same street, and see that one in particular has a lot of cars parked out front. You might assume this means it's the best restaurant, as everyone's eating there, and you pick this over the others. This would be an example of positive network externality for this business that you chose. Its high demand has led to more demand. On the other hand, you might have a different view, and see that restaurants with all the cars out front mean that they're busy, and that you choose another restaurant on the street over this one. This would be an example of a negative network externality. The business with the high demand is now losing business because people think it's too busy. A more information systems related example might be you choosing to use Discord over something like a Facebook group chat, as all your friends are on Discord. Again, this would be an example of a positive network externality. Now, if you've been paying attention, this might sound all a little bit familiar. This is a closely related concept to that of the network effect. The network effect states that the value of a network grows with the number of participants. In fact, many sources, such as our textbook, use these terms interchangeably. However, I'd say that network externality is more of a general economics term that describes the product's demand, while the network effect is a specific case of positive network externality. Regardless of the terminology we're using, what's important for us is that a network, or for a network rather, to be successful, it must reach a point of critical mass where its popularity starts exploding on its own. We sometimes call this point as going viral. It's often something we see with social media sites like Facebook. They start very small and offer limited value, as there's no one really to interact with. Then they start growing to a tipping point where the popularity and use become so prolific that you're almost forced to participate to stay in contact and update with all of your friends and contacts. This growth is not permanent, however. Growth eventually leads to congestion problems, which can only be solved by expensive investments in IT. The market also eventually becomes saturated. You run out of people willing to sign up, and competitors start emerging. There's also often a dilution effect, whereas as a network grows, its original purpose becomes more diluted and generalized. It in effect loses what made it special. Facebook, for example, started as a site targeting only university students and enabled topical discussions of what was relevant to them, namely school and university. However, as Facebook grew, it became more diluted and started targeting a more general audience. Nowadays, your parents and grandparents are probably on Facebook, as well as your younger siblings. Facebook has transformed from a niche service for university students into a completely different tool. For those original users, Facebook no longer provides that same original benefit it started with. The same thing can happen for a business if growth of your network is not closely managed and targeted at a specific business goal. Let's now move on to talking specifically about computer networks and the IT side of things. By IT in this case, we mean the technology that actually powers the computer networks. But first, we should define what a computer network is. Computer networks are collections of computers that communicate with each other over transmission media. What are transmission media? Well, there's a few different common ones that we see. The first are physical media like copper cables and optical fiber cables. The most common of these that you probably see in everyday life are Ethernet cables, like this Category 6, or Cat6 for short, Ethernet cable that I'm showing now on the screen. So here I have a pretty standard example of an Ethernet cable. This would be an example of a physical transmission media, in particular one that uses copper conductors to transmit data. This one in particular is a Category 6, and that category system basically describes the type of insulation and conductors that are inside the cable. Normally higher categories mean that they have better insulation, that means there's less resistance in the cables, and it means that they're more resistant to electromagnetic interference. The better the insulation is, the better the conductors are, the more bandwidth the cable will have. That means the more data it can transmit per second. A Category 6 cable like this tends to get about a gigabit per second, but it can go up to 10 gigabits per second when it's over a very short distance. On the end here, we have a particular type of jack called an RJ45, or a registered jack 45, and this is the standard connector that you see on most laptops and routers and things like that. It just sort of clicks right in, and then you're connected to the network, at least if everything went correctly. Inside a cable like this are actually 8 conductors. Let's take a look at that now. So here I got some handy scissors, and we'll open it right up. See that a little bit. There should be 8 little wires in there, and I will just strip it for us so we can get a better look. So you'll notice that they are twisted together. This just helps improve the resistance to electromagnetic interference. And we have a central piece of plastic that just keeps them separated and in place. So we got 1, 2, 3, 4, 5, 6, 7, 8. And it transmits data over these by basically setting each wire to a high or low voltage. For example, a high voltage, like 2 volts, might represent a 1-bit, and the low voltage, like -2 volts, might represent a 0-bit. This is a bit of an oversimplification, but the essential idea here is that we can encode data by changing the voltage on these wires from high, like 2 volts, to low, to -2 volts, and this allows us to encode binary data like we saw in the hardware lecture. Newer standards like Cat7 and Cat8 can get similar speeds, but over greater distances, as they have less degradation of the signal, and in some cases can even get up to 40 gigabytes per second over a very short distance. This now brings us to optical fiber cables. These are cables that are mostly used in data centers and in the backbone of the internet to provide even faster speeds and avoid electromagnetic interference. So here I have an example of a fiber optic cable. You can see a little bit closer up over here. And the idea with this is that it's hard to see, but there are tiny little glass tubes. This one has 2 of them, and light goes into these little glass tubes and down these cables. This one has 2 joined together until they get to the other side, and then the light comes out here. What these are is there's going to be a glass tube through the cable. It's going to be surrounded by a reflective material to keep the light bouncing inside of it, and then an outer plastic layer. So the light goes in, it keeps bouncing through the cable until it gets to the end and goes out here. The idea here is that we can transmit data using light. So if there's light, it might be a 1, and if there's no light, it might be a 0. And just like Category 6 cables, these have different sort of standardizations and qualities with them. This one in particular is an OM5 cable, and that can get us up to about 100 gigabits per second over a very short distance. So this is a short cable. This type of cable is aimed more like connecting a router and a switch together. You also tend to see fiber optic cables that are aimed more at going over very long distances, even things like under the ocean. So we tend not to see these types of cables used too much for home applications, and that's because the equipment that uses them tends to be a lot more professional grade and expensive. But they are something you'd see if you're working in a data center. So just taking a look at this cable on its own isn't too interesting, so let's actually test it out a little bit. And to do this, I have a little tool here. And what this is a fancy laser pointer. That's essentially just a laser pointer, but on the top, it has a little adapter to connect it to a fiber optic cable. And this is an actual tool used in industry to test these cables. If you want to make sure your cable's good, you plug this into one side and see if you get light out the other side. that's exactly what we're going to do. But before we begin, one thing I should mention is whenever we're using lasers like this, it's always important to use the proper eye protection. So here I have some glasses, and these are properly designed, at least the coloring and the tint, to block specifically the wavelength of this laser pointer. So if you're doing anything with lasers, make sure that you have the correct eye protection, and they have to be the right ones for the frequency that your laser uses. So let's get into this. So first I'm going to open it up, and we're going to put a little adapter on to match this cable type. And then we can hook the cable in just like that. So what this is going to do is it's going to send a laser through the wire. So I have it turned on now, and I'm going to move the light away just so we can see it clearly. And we can already see it coming out there a little bit. So notice that even though this cable is all kind of twisted and turned about, we're still getting a nice laser coming out the other end. The reason for this is, as I mentioned, there is a coating in here that's reflective, so the light sort of bounces along the tube and coming out at the end. So the way the computer can use this to actually transmit data is if we stop just putting a solid light, we could actually encode data, for example, as the light being on as a 1 or the light being off as a 0. And I have it really slow here, just in sort of a testing pattern, but in real life this would flicker extremely fast, faster than we could probably even perceive with our naked eye, and transmit data to the computer. We also have 2 of these, so we could have bidirectional data or be sending a lot of data in one direction. And it's interesting because it's still coming out quite powerful. You can actually see that it's very directional. If I have it up at all like this, you can't see any light coming out. It has to be actually hitting something to see it. So it's essentially now a little laser pointer coming out of here. Okay, let's now move on to our next category of transmission media, which will be wireless transmission media. And I don't think I'm going to need these for that. You're probably most familiar with wireless network technology such as Wi-Fi, cellular networks, and Bluetooth. These use radio frequencies to transmit data as radio waves. This can be coded in different ways, such as amplitude modulation, or AM, where the high amplitude denotes a 1 and the low amplitude denotes a 0. Or it can be encoded as frequency modulation, or FM, where low frequencies are encoded as 1s and high frequencies as 0s. Again, these are a bit of an oversimplification, as modern Wi-Fi and cellular networks now use more complex and hybrid approaches. But the essential idea is the same, using radio waves to encode data. Light can also be used in a similar way to transmit data wirelessly through the air. And the technology you're most familiar with that does this, that you probably use in everyday life, is your TV remote. TV remotes use infrared light to tell your TV to change the channel. They do this by sending out pulses of infrared light. Certain pulses might mean change the channel, turn up the volume, or change the input you're on, and so on, based on the sequence of the pulses produced by the remote. This technology used to be a lot more common in consumer laptops in the 90s. Most laptops in this era would come with an IR port, or an infrared port, for sharing data directly with another device like a printer, a cell phone, or another laptop directly. Key thing here is that unlike your remote, this communication was bidirectional. It went both ways. In the 90s, even handheld gaming consoles, like this little Game Boy Color here, had infrared ports for either playing local multiplayer or more commonly transmitting data between them. So let's take a quick look at how this would work. So I've got 2 Game Boy Colors here, and if you take a look at the top of this one, we can see this little black box. So what this is, it's a little piece of plastic that blocks all light except for infrared light. To us, this just looks black because we don't see infrared. Behind it, there's an infrared LED for transmitting data and an infrared receiver for receiving data. So, for example, if you wanted to send your high scores to your friend, you'd have to take both the Game Boys, get the game working, and get it ready, and then line them up like this, just so the infrared ports are facing directly at each other. And then data would be transmitted between them. The big problem with this is that it was slow, and if something like this would happen, where it's just slightly moved, the ports are now not lined up, so they need a direct line of sight and not moving during that slow transfer process. So for reasons like this, they were quickly displaced by other technology, namely things like Wi-Fi and Bluetooth. They transmitted data over radio waves instead of light, so that means you didn't have to be directly pointing at someone, and it made things like multiplayer more practical. Can you imagine having to play a game where they're both facing each other like this, and if you move at all, the game disconnects? Wouldn't be that fun. which is why these commonly were just used for transmitting data like high scores, maybe a Pokemon, or some part of your save file, as opposed to actually live gameplay. Regardless of the transmission medium used, we can classify computer networks into a few different types based on their size and the area they serve. And this is summarized nicely in this table from your textbook. The first are personal area networks, or PAN for short. These are the networks that are connected to and relating to a single person or individual. This is a new kind of network that's still emerging through things like wearables such as smartwatches and AR headsets. But it's also common in the medical setting, where a patient might have multiple medical devices and the sensors attached to them that communicate directly with each other, or something like a nursing station. The key here is that there's only one real user of these networks, and they're the single topic of the network. And the devices are located very closely together, normally within 10 meters or directly attached to the user of the network. The next are local area networks, or LANs. These are computers or other devices that are connected together at a single site or physical location. This is the type of network you might be most familiar with, without even realizing it. Your home Wi-Fi router and the devices you connect to it, whether through a physical cable or wirelessly, form a local area network of just your devices in your home. This can include computers and laptops, but also things like cell phones, using Wi-Fi, IoT devices, and smart thermostats and security cameras, as well as things like gaming consoles and smart TVs. Your LAN is how you share a single internet connection with all of your devices. LANs can also be larger in scale, like the network for a whole office building that has hundreds of users and devices. The key here is that LANs are local to a single site, normally isolated from the wider internet, and are only used by a single entity comprised of multiple users, such as a business or your own household. They typically use Wi-Fi or Ethernet cables to connect devices, and they don't extend past a single building or campus. Western's internal network on their main campus can be described as a LAN, or local area network. And this brings us to wide area networks, or WANs. Wide area networks connect two remote sites. For example, connecting a main campus or office building to a remote satellite campus or remote satellite office. A real-world example would be the Orion network, which stands for the Ontario Research and Innovation Optical Network. This is a high-speed wide area network for research and education that connects most of Ontario's research and educational institutions together with a high-speed fiber optic cables. These types of networks tend to cover large distances, so they are primarily concerned with data transmission speeds and reliability. As such, they tend to use mostly fiber optical lines. The key here is that they join multiple remote sites together and cover large distances. The sites they connect are normally private and belong to one organization or business. However, they may also be joined together as part of some greater alliance or collaborative effort, such as the case of the Orion network. Recall that the value of a network increases with the number of participants, so it makes sense for organizations that are not in direct competition with each other to cooperate in this way. Even in cases when there is some level of competition, the advantages of working together can still be greater and offer greater value for the business than simply being left out of the network, and that would simply be too costly than the alternative. The last one are internets. And I think everyone's familiar with the internet, spelled with a capital I. These are networks of networks that connect multiple networks together. They tend to be different from wide area networks in that they are public or access is offered to them as a paid service, sort of like how you pay your ISP to connect to the internet. One organization does not own all the devices in the network or all of the network infrastructure. The main internet that we think of, the one that was spelled with a capital I, is a general-purpose public internet that connects us to businesses, services, and other persons for a large variety of uses and reasons. However, there are other internets, such as Canary, that are more specific to their intended purpose. Canary is the Canadian Network for Advancement of Research, Industry, and Education, and connects all of the provincial research and educational networks together in Canada, including Orion. Canary provides the backbone network for these research networks to communicate with each other, but does not own or operate the individual networks it connects, like Orion. The key here is the internets connect networks together, and they cross organizational boundaries. Finally, let's move on to the topic of cloud computing. Let's start by actually defining what cloud computing is, as it's a rather confusing marketing term in most cases. Our textbook definition of cloud computing is the elastic leasing of pooled computer resources over the internet. But what does that actually mean? Well, before we get into what cloud computing is, it might be easiest to first explain how things worked before the cloud was around. The cloud started merging in around 2010, but before that we did things much differently. In the traditional method of providing an internet-based service or hosting a website, an organization would build their own data center and purchase their own servers like this one here. For example, let's say that this server is providing a basic business website for a car company and contains information about their products, some video ads, and maybe even a virtual tour of their cars. At first, this is fine to be run from one server like this, in a small data center that the company built, though in this case it's probably more like a server closet, as the demand on their website is still low, as we can see here in the graph. However, as they start marketing their cars more, and start offering customer services and support for their website, demand picks up and they need to add more servers. So far, not a big problem, they can just buy more servers. There's this big initial rush of existing customers to register their cars in the new customer support portal, but that demand quickly dies down after most of the customers have finished registering their cars. But this does raise a little bit of a problem at this point. The company bought 2 new servers, but after this initial demand of customers registering their cars, one of the servers sits idle, with little to do other than use up energy and space. Still, the company moves on to start running TV ads, and they notice fairly quickly that the demand on their website correlates directly to when the ads are played on TV. The ads contain a link to their website, and when customers or potential customers see that ad, they tend to go to the website to check it out. But again, here's a problem. When the ads play, the demand on the site is more than what the servers can bear. But when the ad is done playing, demand drops, and the third server is once again idle. So once again, the company is forced to buy additional servers, as simply having the site go down during periods of high demand is not an option. They see having extra servers as an unavoidable cost of doing business. These extra servers also provide some redundancy in periods of low demand, as if one of the servers break, they simply redirect traffic to the working server. But there's even a bigger problem coming. Marketing has just decided to run a Super Bowl ad that will feature their newest line of cars and direct all the potential customers to their website to view a new virtual tour of the new car. The IT department panics a little bit when they hear this. They know that the ad will be displayed to millions of potential customers, and that virtual tour feature of the website uses a large amount of bandwidth. If the ad ran right now, the campaign would be a massive failure, as their site could not handle all the traffic, and customers would simply get an error message when viewing the site. This would most likely mean that they're just going to leave and not really look into the car any further, which means you lose sales. So IT does the only thing they can in this case, which is buy more servers and networking hardware. The campaign is a massive success, but now we have a big problem on our hands. The campaign's over now, and the demand on the site has fallen back to normal levels. But now, IT has a room full of servers that are not being used at all. These extra servers cost money to maintain and keep powered on. But even worse, they can't get rid of them. Or they won't. Why? Because being able to meet future demands is important. Marketing at any time could choose to do another one of these large campaigns. In the past, this was just the cost of doing business, and there are a few options to mitigate these costs. But now with cloud computing, which came about in the early 2010s, there is a potential solution. Cloud computing seeks to offer a solution to this kind of demand problem. In the cloud computing model, businesses no longer build and maintain their own data centers, but instead lease servers from a cloud provider. However, this is not your traditional kind of lease or rental agreement. It's elastic. This means that businesses can request more or fewer servers on demand, and also change the specifications of those servers and the resources they have allocated on demand. And by on demand, I do mean in real time. The business could scale their server allocations up and down in real time to meet their current needs. And by current needs, I mean like right at that second. Or they could add more hard drive space, RAM, or number of CPUs as they need fit, if they need them to be faster, or they need to store more data. That sounds cool, but how is this possible? How can whole new servers be set up in seconds, or more resources be added on demand? Well, this is made possible through virtualization. Recall from Chapter 4 when we talked about virtual machines. Cloud providers use the same technology to create virtual servers that appear to the outside world as real servers, but they're actually virtual machines. Let's take a look at how this would work. We'll be using the same car company example as before, except this time, rather than running their own servers, they're leasing them from a cloud provider. Right now, the servers are shown on the screen are not the car companies, but the cloud providers. When the car company makes a request from the cloud provider to allocate servers for them, the cloud provider creates one or more virtual machines with the data and software on them provided by the car company. This is fine for the normal amount of traffic, but what happens when the demand increases? As demand increases, the car company asks the cloud provider to start up more virtual machines. The car company only pays for virtual servers it's currently running, and there's normally no setup fee or startup cost to start a new virtual server. If the demand spikes yet again, like during that Super Bowl campaign, the car company can once again have the cloud provider start more virtual machines. From the cloud provider's point of view, these virtual machines might be running on different physical servers, or even in different data centers. But from the car company's point of view, they all act like real servers that are accessible over the internet. So far, so good. We have scaled up the demand, but where the real magic starts coming in is when the demand goes away, like after the Super Bowl campaign is finished. Once the demand has died down, the car company can now ask the cloud provider to stop the unneeded virtual machines. Since the car company is only paying for the time and bandwidth they use, they no longer have to pay for the servers they don't need or are currently running. What makes this all even better is that the scaling up and down can be fully automated and does not necessarily need human intervention. A new server can be automatically started when demand rises and shut down when it's not needed. So that's great for the car company, but what's in it for the cloud provider? They still need to buy and maintain the servers and run the data center after all. Well, the advantage for the cloud provider is that they can pool the resources and rent out parts of this pool to individual companies. For example, we might say that these two virtual machines are for the car company. But the cloud provider can still rent out unallocated resources on the physical server to more companies. For example, maybe Netflix is also using a few virtual machines on the same physical server. For the cloud users, these servers are completely isolated and they have no knowledge of what other virtual machines may be running on the same physical server. For the cloud provider, they're maximizing the use of their hardware and able to rent out physical servers in parts rather than as a whole. If the car company then wanted another virtual machine, the provider could simply start up a new virtual machine on the next physical server if the last one was full, and there'd be no noticeable difference to the car company. From a cloud user's perspective, the resources are endless, and they just pay more when they need more. We just went over a lot in that example, so let's summarize. Cloud computing is the elastic leasing of pooled computing resources over the internet. By elastic, we mean that leased computing resources can be scaled up or down dynamically in real time. This is not a static lease that you have to wait to expire to renew. At any time, you can add more resources, usually with no penalty. This scaling can be done manually by a person or fully automated based on current demand. The other key term here is pooled. By pooled, we mean that the physical resources are shared by many different organizations. One physical server could host multiple virtual servers, each used by different organizations. Or one hard disk could be divided into space used by multiple persons. For example, when you use something like OneDrive or Google Drive, it may appear that you have your own virtual hard drive, but in reality, these files share the same physical hard drive as many other users. In fact, your files may actually be spread across multiple physical hard drives and servers, but only appear as one single storage space on your own computer. This pooling of resources allows for cloud providers to take advantage of the economics of scale. That is to say that they can get hardware for cheaper when buying in bulk than a regular business could when they're just buying a few servers. This allows the cloud provider to offer these services cheaper than what businesses could do when setting it up on their own. The last key term here is over the internet. These virtualized resources can be allocated programmatically using standard web services over the internet as needed. Since the web services used to allocate and provision the servers are standardized, anyone can read the documentation and start developing software for the cloud. There's no need for meetings to discuss requirements, specifications, or special contracts between the cloud provider and business. The business just creates an account and starts deploying their software and services. Okay, so that sounds great so far, but how does this all stack up against traditional approaches, such as buying and running your own servers? First, let's discuss the positives of cloud computing that we've already mentioned so far. So in cloud computing, we have a low initial investment, since you don't have to buy the server. We have somewhat rapid development. There's standardized web services, so all the documentation is already there if we want to build something for the cloud. We have dynamic scalability. We can add or remove servers to meet our demand. There's known costs. Usually the cloud provider has pretty standardized fee structures, so it's not going to be a surprise like with your own data center if you suddenly have to buy another server. The cloud provider also provides a level of security and redundancy. If all your files are on the cloud provider is the one handling the backups, for example. However, a key point here is that it's only really secure if you trust your cloud provider. You are sending all your files to the cloud, so that means in theory the cloud provider could have access to those. You're also really trusting them to properly back up your files. There's also no obsolescence or depreciation. Since you don't own the physical server, you don't have to worry about it becoming out of date. That's all going to be on the cloud provider. And there's also the economics of scale, which mean that in theory, everything should be cheaper than actually buying your own servers and networking equipment. So let's talk about some of the cons of the traditional approach. This would be like actually hosting your own servers in-house. So there's that significant initial investment. You have to buy up all those servers up front, as well as the networking hardware and stuff like that. So you're going to be paying a lot of money up front. There's also going to be maintenance costs. So you still don't get away from those recurring payments. You're going to have to be paying employees to maintain those servers. You're going to have to be dealing with them when they become obsolete or break, and you're going to have someone there monitoring everything. And that ties into the support costs as well. It's also difficult to accommodate any changes in demand. Like we saw in those examples, if you suddenly have more demand, your only real option is to buy more servers. And when demand drops, you can't really get rid of the servers. At best, you can turn them off so they don't use power, but they're still physically sitting there depreciating in value and needing maintenance. There's also physical space requirements. Servers take up a lot of space and a lot of supporting equipment. They need to be properly air conditioned, they need to have fire suppression systems and things like that. So this is going to take up a big chunk of real estate in your business. And then there's the issue of obsolescence and depreciation. Servers don't last forever. They're eventually going to become out of date or die, and that means you're going to be having to replace them if you're hosting them yourself. But the cloud's not without its cons either. First, you have loss of control over the data. You're sending all your business's data to some cloud provider, and if you don't trust that cloud provider, that could be a big problem. The other big issue here is that there's a lot of privacy laws that dictate who you can send your data to about your customers, especially in education and medical type fields. In some cases, the cloud provider might meet those regulations. In other cases, it might not, and you might be forced to host that data in-house. So the data is also, when it's stored on the cloud, is no longer on site. That means it's going to be slower and harder to access. So for example, if you wanted to back up all your data, that might run fast, like the files might copy fast onto the cloud provider, but you still have to get that data back to your own business. And if you don't have the best internet connection, that could take some time. Usually that's not that big of a deal because you're not really processing the data off the cloud, you're doing all that on the cloud. But if you ever needed to dump everything down or move to another cloud, there is going to be significant effort to actually move that data around. And you also have to rebuild existing software and processes to match the cloud. Some software isn't going to run well on the cloud, and it might need to be redesigned. That's going to have costs associated with it to hire developers to do those changes, and it could also mean process changes for your business. And that could mean retraining employees. There's also a few pros to hosting things in your own business, in-house that is. So in this case, you'd have your own servers, which means you have full control over your own data. This might help to comply with privacy laws, as we mentioned. The data is also going to be local, so it means it's going to be faster to access. If you have some complex data analytics you want to do, your data is right there for it. You don't have to worry about downloading it and uploading it to the cloud. And you don't need to trust a third party for any security or redundancy. That's a bit of a double-edged sword. If you're competent in doing that, that's great. You can ensure that's done right. But if your business has nothing to do with computers, and you're not really sure about how to properly do security and redundancy, that could actually quickly turn into a con. So far, the cloud services we've been discussing have been infrastructure services, or as they're commonly called, infrastructure as a service, or IaaS. IaaS provides the most basic building blocks to build a cloud solution. These would be the bare virtual machines or virtual storage solutions we've been discussing so far, where a company can dynamically allocate new computing resources. In this case, it's up to the user of these services, that would be the business, to provide the operating system for the virtual servers, the software, and the data to store and manage when new resources are allocated. So that means you have to choose when you're adding more servers. It also means that you have to provide your own operating system and software. Cloud providers just going to give you the bare bones virtual machine or a place to store files, and it's up to you to figure out how to use them effectively and efficiently. This type of solution is great if you've already developed your server software and information systems and simply want to move it to the cloud. They're also useful if you want to build a very customized solution. Some examples of IaaS providers are Amazon Elastic Compute Cloud, or sometimes called Amazon EC2, Amazon Simple Storage Service, also called Amazon S3, and Rackspace's cloud offerings. Amazon EC2 provides virtual machines on demand, and Amazon S3 provides cloud storage. Rackspace provides similar offerings to Amazon, but with the option for private and hybrid clouds, which we'll get into in a bit. The next level up in our hierarchy of cloud services are platforms as a service, or PaaS. The reason why this is a hierarchy, or sometimes called a stack of services, is that each level is built on the last level. PaaS builds on IaaS and provides not only the bare virtual machines and storage, but also most of the software, including the operating system, database management system, server software, common tools, and management of the allocation of virtual machines and resources. All you need to provide is your own custom application that you want to run on the cloud. This is a great option if you're developing a new application that's targeting a specific cloud platform, such as maybe Microsoft's Azure. This would be an example of a common PaaS product. The downside is that you might be locked into this platform after you've developed your application for it. Things like the APIs you're using and some of the specific libraries might be very specific to that cloud provider, and you can't simply change to another one. This is an example of the lock-in effect that we talked about earlier in past lectures. Another example of PaaS products is Oracle On Demand, which provides a server with an Oracle DBMS, a database management system, pre-installed. So on the top of our cloud service stack is Software as a Service, or SaaS. These are the applications that run on the cloud and provide services to end users that would traditionally be desktop applications. You have likely seen these services without actually even knowing that they are software as a service examples. For example, Gmail and the web versions of Outlook provide a web-based email client. Years ago, you'd have to check your email using a desktop application that connected to a remote server. Now most people use a cloud-based application that they access through a web browser that provides both email client and the email service in the same location. These are both examples of a SaaS application. Second example would be cloud storage applications that target end users directly, such as OneDrive, Dropbox, and Apple's iCloud. It's starting to become more common to see software vendors that traditionally targeted desktop markets to start moving their offerings to software as a service. Big advantage of this for the vendor is that they can now move their product from being a one-time purchase to being a recurring subscription. We see offerings such as Microsoft Office and Adobe Software Suite being moved to a software as a service model. And this means that they're going to start being offered both as a service and as a web-based application that you use for your browser. For example, there's now web-based versions of Excel and Word that you can use directly through your browser. And if you're interested in these, you should have access to them for free as a Western student. For customers, this potentially has advantages in terms of never having to upgrade their software or pay for a new version, having the convenience of using the software anywhere through a web browser, and storing their files on the cloud so they're always accessible so long as you have an internet connection. The downside is loss of control of your data and now having to pay a monthly subscription fee. So the big downsides of cloud computing that we discussed are giving up control of your data. You're essentially sending all of this data that your company has to a third party, cloud provider, and over the open internet. Recall that information is your business's greatest resource, and we're talking here about handing all of that information over to someone else to manage. Having your data and information stolen is not the only risk. Imagine someone getting access to your business's website. They could potentially post something inappropriate or defaming, and that content would hurt your relationship with your customers and suppliers. Or they could use your computing resources for malicious or illegal activities. Even if we fully trust the cloud provider, a big risk is getting your data to and from the cloud securely. Here we see a diagram of what this process would normally be. You have your business's local area network with all the employees, devices, and your local computing resources, and you need to transmit your data to the cloud provider. In this case, let's say that we want to send a spreadsheet, just for the sake of the example. To do this, or to even connect to the internet at all, we need to have the services of an internet service provider, or an ISP. These are companies such as Rogers, Bell, or TechSavvy, which connect businesses and home users to the internet for a fee. All the data that we wish to send or receive through the internet has to pass through our ISP, and this is our first problem. If this data is unencrypted, an untrustworthy ISP could copy the sensitive data, or even worse, alter it in a malicious way. Now, if we have a commercial ISP, we're probably going to be pretty trustworthy. But what if you're working from an internet cafe or a hotel? You might not know much about that network that you're connected to, or the ISP that you're using, and there's a lot higher chance that it could be untrustworthy. So the next step in this process is for your ISP to route your data through the internet to the cloud provider. And this is where things get complicated. While this is shown as a straight line in this diagram, the route your data will take through the internet is not always the same or entirely in your control. In fact, your spreadsheet might even be split up into smaller data fragments and sent through all kinds of different routes, and then be reassembled at its destination. This poses another problem, as if you don't know where your data is traveling through the internet, you don't know who could have the opportunity to snoop on it or alter your spreadsheet. So how do we prevent this? Well, luckily the internet is starting to evolve and encryption is slowly becoming more standard or even mandatory. However, until encryption becomes the default, there are a combination of strategies and technologies and tools we can employ to use the cloud securely. These include virtual private networks, or VPNs, private clouds, and virtual private clouds. Perhaps the most common and pervasive of these are VPNs, which are frequently used in both business and for personal use. Virtual private networks create a virtual encrypted tunnel through the internet, which gives the appearance and function of two remote networks being joined together locally, even though they are actually geographically remote. To explore this, let's take a look at an example. Let's say your business has a main office in London, Ontario, but they also have a remote satellite office in Thunder Bay, Ontario. Due to the distance between these cities and the high cost of running fiber, using a traditional wide area network to connect your offices is not possible. So you're going to be forced to connect them through the public internet. As we just explained, this has significant security issues, if our data is not encrypted. It also makes it hard for an employee at the satellite office to access a computing resource at our main office, like remotely connecting to their desktop PC at the main office from the satellite office, as most LANs try to isolate the internal devices as much as possible from the wider public internet. A potential solution to this is to use a virtual private network to create an encrypted tunnel through the internet. Now when we want to send data, a spreadsheet, or anything else to our satellite campus, the data is encrypted as it leaves our local area network. Next, when it finally arrives at our satellite campus, the encryption is automatically removed, and the file is sent on to whatever device it was being sent to as normal. From the perspective of devices in our LANs, both the remote satellite office and our main office, it appears as if all these computers were in the same network, and that the encryption is done seamlessly and automatically, so the devices aren't even aware of it. The same concept can also be used for remote individual users working from home, hotels, or even things like coffee shops. And most importantly for our current topic, it can be used to connect with a local cloud provider. When we set up a VPN in this way, our communications with the provider are secured, and from the perspective of our devices on our local area network, the virtual machines and cloud services appear to actually be on our local network, or LAN. One thing I'll quickly also mention is that the type of VPNs that we've been talking about here are a little bit different than what you might have seen advertised in places like YouTube. The VPNs we've been looking at are between businesses and connect remote networks together in a transparent way. The VPN services that we see advertised online are more personal VPNs. Rather than connecting you to a remote network, they connect you to the VPN provider, which in turn connects you back to the internet. Now, why would anyone want to do this? It's kind of like going a long way back just to get to the internet. Well, the VPN providers lift off a long list of security reasons and benefits for this in their ads. These are things like protecting your passwords or stopping hackers, but unfortunately most of these claims are actually pretty dubious at best. That's not to say that they don't have some purpose. What this kind of setup is doing is two things. First, it's hiding your traffic from your ISP, and second, it's hiding the source of your traffic from the service you're connecting to. This means that the websites, games, or chat rooms, or so on that you're connected to will not know who you are or where you're connecting from unless you provide this information to them in some other way. So this setup might help you stay anonymous online, at least in theory, but the big problem here is that while your ISP can't snoop on you, your VPN provider sure can. So your VPN provider, after all, is getting all your traffic and encrypting it for you on your behalf so it can route it onto the internet. And that means they have your raw unencrypted data. And as your ISP is located in Canada, that means they're bound by Canadian privacy laws. Your VPN provider, not necessarily. They could be located anywhere in the world, and they're far more likely to be malicious, especially if you just found them through a random internet ad. A secondary issue is that you're not tracked online just by your IP address, and that's what this setup is hiding. You're also tracked based on things like fingerprinting, cookies, sessions, emails, and accounts, and your VPN provider is not going to do anything to hide those. So why do people keep using these services? And by these services, I mean specifically these personal VPNs and not the business ones. Well, some people are taken in by the false advertising and scare tactics, but I think most of them use them to get around things like geo-restrictions and censorship. For example, if Netflix thinks that you're connecting from the USA, you'll get a very different selection of shows to watch than if you're connecting from Canada or the UK. These private VPN providers allow you to fake the location you're connecting from and bypass any geo-restrictions like these. They can also bypass most types of internet filtering or censorship, and allow citizens from countries with more restricted free speech laws to access content that might be prohibited locally. In any case, the key takeaway here is that the way we use VPNs in business is different from these personal VPN services you might be familiar with. Business VPNs normally connect remote local area networks together over the internet to ensure secure remote work and data transfers, while personal VPN services connect you back to the internet in an effort to sort of hide your identity a bit or bypass geo-restrictions. The next technology we briefly mentioned for securing the cloud was private clouds. These are exactly what they sound like. Companies set up their own data center, servers, and virtualization technology to create a cloud that's only used by that organization. You might be asking, why would you do that? It eliminates all the benefits of using a cloud computing in the first place. And now you have to pay for your own servers and all the overhead of running them. And you'd be correct, which is why these tend to be rare and mostly only seen in very large organizations. For example, universities like Western Ontario are starting to create their own private clouds, as they have frequent need for new servers to be allocated to different departments for research or educational purposes. These virtual servers might be scaled or shut down when they're no longer needed, such as, for example, a course that needs a server until the course ends, and the resources are then allocated to new departments. For a large organization like Western, this makes sense as it eliminates a lot of the overhead of setting up new physical servers each time like a course starts up and needs it, or a research project. A second reason an organization might use a private cloud is for security and privacy reasons. In some cases, laws prohibit or severely limit the sharing of sensitive information with third parties. This is common in healthcare, for example. Large organizations in these sectors that commonly handle sensitive information may need a completely private cloud to comply with data privacy laws. As an added benefit, if your organization does successfully set up a private cloud, they can then rent out the unused resources to other companies. This is actually how companies like Amazon got into cloud computing game in the first place. They had to essentially build their own private clouds just to run their own e-commerce site, but quickly found that renting out the unused resources was very profitable. In fact, Amazon now makes more money selling cloud services than they do for any kind of online retail sales. And this brings us to the last technology mentioned for securing the cloud. virtual private clouds, or VPC. These use public cloud computing infrastructure, but with highly restricted access controls to isolate any resources from the wider public cloud. Basically, resources are reserved for the VPC, and pooling of resources is not performed when it would be an issue for sensitive data. The downside of this is that you will pay more to reserve these resources, and you're still transmitting your data over the internet, hopefully encrypted in some way. The upside is that you still get the benefits of the dynamic scalability and not having to manage your own data center. And that brings us to the end of our lecture on networks and cloud computing. If you're interested in going into more depth on these topics, in particular in networks and the IT side of things, I highly suggest reading Knowledge Extension 9 in your textbook, which goes into more depth on the underlying technology that powers these networks and talks more about how the cloud actually works. As always, thank you for watching, and have a great day.